All right. So if you were here or not here yesterday, we were talking about functions. We were talking about one-to-one functions, and we were talking about on-to functions. So first of all, I just want to remind everybody, I'm just going to have us take some notes off to the side here. Just as a quick recap, I'm going to give you hopefully some very straightforward ways of remembering things. So let's say write this down, a relation. This is at the top of page 5 over to the right-hand side. A relation is a function if all x values are different. That's probably the easiest way to remember how to figure out if something is a function. If all the x values are different, those xy pairs, whatever it is a function. In terms of a visual perspective, you can use the vertical line test. If it crosses more than one point at the same time, it is not a function. If it only touches one point at a time, it is a function, which means all of the x values are different. Next one. A function, so once you've established that you have a function is one-to-one if, anybody think of an easy way to explain this one based on yesterday's notes? You think about that for a second. I'm going to take another bite of my breakfast. You check in on your notes from yesterday as well. How do we know if something is one-to-one? Yeah, Lilia? Yep. If each value is paired with only one y value, that would be like the technical definition. Maybe an easier way to think about it is what that means is if all y values are different. So if all the x values are different, you have a function. Once you establish that you have a function, if you want to know if that function is one-to-one, all of the y values must be different. Visually, that would be the horizontal line test. If the function touches 2 points on a horizontal line, it's still a function. That function is not one-to-one, though. If that function only ever touches 1 point with the horizontal line, then that function is one-to-one. Last one. A function is on-to if I think the best way to do this is what was written on yesterday's notes from page 3. If the codomain, what is our normal assumed codomain? All real numbers. Okay. So if the codomain, I'm going to put in parentheses here, usually all real numbers. Not always, but most of the time, we're just going to assume that the codomain is all real numbers because those would be the possible values of y until we actually figure out the actual values of y. So a function is onto if the codomain, which is usually all real numbers, is equal to what? Go back to page 3 if you don't know. It's on that. That's the last sentence of the last paragraph before example 1 on page 3. The codomain is equal to the range. Yeah. If the assumed values of y, the codomain, if all those values are equal to the actual values of y, the range, that would make it an onto function. So those are the three big things that we talked about yesterday. Today, we're going to continue those ideas, but we're going to add in a few other things. So we're going to start off today's notes by talking about, at the bottom of page 5, discrete and continuous functions. This is something in Algebra 1 that I usually talk about very, very briefly. So if you haven't heard this before, because you didn't take an Algebra 1 class from me, or if you don't remember it, that's fine. I talk about it maybe one time in Algebra 1. The nice thing about discrete versus continuous is that this, I think, is a lot easier to understand than one-to-one versus onto. So functions can be discrete, continuous, or neither. If it's neither, we could call it discontinuous. Real-world situations where only some numbers are reasonable are modeled by discrete functions. Discrete functions are basically represented by individual points on a graph, like a scatter plot. That would be a discrete function. Situations where all real numbers are reasonable are modeled by continuous functions. So, for example, this would be a continuous function from yesterday because everything's connected. It makes like a curve or a line or whatever it is. That's a continuous function. And then the ones that we were talking about with the gold medals or the medals from the Olympics, this would be a discrete function because those are individual points that you would put on a graph. You would not connect them if you made a graph. You would make a scatter plot. So that's going to be the difference between discrete versus continuous. So a continuous function is graphed with a line or an unbroken curve. Unbroken in that it is continuous all the way through. A function that is not continuous is a discontinuous function. So discontinuous just means not continuous. So discrete functions are types of discontinuous functions, but they're a specific type. So a discrete function is a discontinuous function where the points are not connected, like ever. A function that is neither discrete nor continuous may have a graph in which some points are connected, but it is not continuous everywhere. So like a mixture of points and lines and curves, or maybe you have a line here and then it stops, but then it picks up again over here and does something like that. That would be neither or discontinuous, just standard discontinuous, but not discrete. Next thing, over to the side here, we do need to talk about intervals. And so there's a study tip. You've dealt with intervals before. Intervals are just like between two values on a graph. We're going to go into more detail with that today as well, but it says that an interval is the set of all real numbers between two given numbers. For example, the interval -2 is less than x, which is less than 5, includes all the values of x that are between -2 and 5, greater than -2, but less than 5. Not equal to either of them because it doesn't have a line underneath the inequality symbol here, but it's between -2 and 5. Intervals can also continue on infinitely in a direction. For example, the interval y is greater than or equal to 1, that basically is like a range that we saw yesterday, would be all the values of y that are either greater than or equal to 1 in an upward direction only. You can use intervals to describe the values of x or y, so domain and range values for which a function exists. And we'll be doing that a lot today as well. So the goal here is to hopefully get through this in a reasonable amount of time, which will allow you for a good amount of work time at the end of class today. Because we didn't really have any yesterday, especially because of the fire drill. All right. Examine the functions. They're going to be determining continuity from graphs. Examine the functions. Determine whether each function is discrete, continuous, or neither discrete nor continuous. Then state the domain and the range of the function. So for the first one, is this an unbroken curve all the way through for the first one here? Are there any holes in it? There's no holes. Okay. So this would be what then? Continuous. Yeah. If it's just a smooth line or a curve, it doesn't break ever, it just continues on, that would be continuous. So continuous. The function is, let's see if we can fit the word continuous in here. The function is continuous. If you need to write it above here, that's fine. It is continuous because the graph of the function is a curve with no breaks or discontinuities. So It doesn't stop, it just keeps going the whole way through. Because the function continues indefinitely to the left and the right, what would the domain be? It goes all the way negative and all the way positive. What's the domain? All real numbers. Any number is possible for the domain. And it even says that right here. It goes all the way left, all the way right. The domain is all real numbers. Because the graph of the function continues indefinitely up and down as well, that means that the range is all real numbers. So that's it for A. We just had to write continuous. A couple other questions here, though. Is this a one-to-one function? No. Not all of the y values are different. If you have a horizontal line, you could cover up more than one point at a time. That is not one-to-one. Is it onto? Yes, it is onto. We just said that the range is all real numbers. It is assumed that the codomain will always be all real numbers unless otherwise stated. And so if we assume that the codomain is all real numbers and it says that the range is all real numbers, those two things match, which means yes, it is onto. Onto means that the codomain is equal to the range. The codomain is always assumed to be all real numbers unless it tells you otherwise. And then since it says right here, the range is all real numbers, that would be equal to the codomain. Since those match, it is onto. Okay, this one here. The function is this continuous? There's a symbol along that line. And the word we're going to use for that is this word right here. That's a break. Because if there's an open circle on a graph, it means we are not including that value. If you remember graphing inequalities on a number line, right? Open circle versus closed circle. Closed means you include it. Open means you do not. And so there's a break at 2, 1. You can also call it a hole, right? There's no value at 2, 1 on this graph. That does not exist on this graph. That's why there's an open circle. So there are continuous sections, but there is a break. So this is not just individual points on a graph, like the third example. It is also not just a smooth line all the way through. So would this be continuous, discrete, or neither? Neither. It does not continue all the way through this hole. That break means that it goes up until that point, it breaks, and then it continues on after that point. So this is neither. So if there is an interruption within a continuous graph, then it's not actually continuous. So because the function is not defined for x equals 2, the domain would be all real numbers except for x equals 2. So any number on the x-axis is valid with the exception of 2. Every value on the y-axis is valid except for y equals 1. So those would be the domain and the range. All values except for x for the domain, all values except for 1 in the range. The last one. These are individual points on a graph. So we look at a continuous, discrete, or neither. Discrete, yeah. If it's just a bunch of points on a graph, like a scatter plot, that function would end up being discrete. So the function is discrete because it is made up of distinct points that are not connected. None of them are connected, it's just individual points, that is discrete. Whenever you have discrete information, the domain are only the x values on the graph. So the only x values that exist on this graph are at -3, -2, 1, 1, -1, +1, 3, and 4. The individual values of x are the domain. You did this stuff, by the way, back in Algebra 1. When you looked at scatter plots like that, you definitely defined domains and ranges based on individual points. The range are all of the y values. So down here at -3, then -2, then +1, +2, +3, and +4. So those individual values for x and y are the domain and the range. We're not going to specify anything to do with all real numbers because you can actually point to each number and say those are the numbers in the domain and those are the numbers in the range. Any questions about continuous versus discrete? Good so far? All right. I do want to go back up to the top here, upper left. I think this is a good question. Does the range of the function need to be all real numbers? The range, the y values. Do the y values have to be all real numbers for a function to be continuous? Does the graph have to be able to go all the way down and all the way up for a graph to be continuous? Here, yes. I hear somebody thinking in the back with their eyes going like this, without words. What do we think? Does the graph have to do that to be continuous on the range? Like a parabola? Yeah, that's a parabola. That's a function. The range is not all real numbers. And it is continuous. So the answer is no. Cool. The function does not need to have a range of all real numbers for it to be continuous. There's a lot of examples of functions being continuous but not having a range of all real numbers. If the range is all real numbers, you're pretty much guaranteed that it's an onto function. But onto doesn't necessarily mean that it isn't continuous or is continuous. So, all right. This is always a good idea. If you're having trouble determining the continuity of a function and you don't have a graph, try graphing it so you can see it. Oftentimes seeing it will make it a lot easier to deal with. All right. Moving on. Now we get to determine continuity based on, in this case, a table of values from a coffee shop. So we're going to think about this one. All right. So determining continuity. It says determine whether the function that models the cost of coffee beans is discrete, continuous, or neither discrete nor continuous. Then state the domain and the range of the function. So let's look at the table first. So if you go to this coffee shop, you're going to see this sign. We're talking about buying coffee beans. So you can buy coffee beans. If you buy up to 2 pounds, it's going to cost you $8 a pound. If you buy 2.5 pounds worth of coffee, it's $20. If you buy 3 pounds of coffee, it's $22. And if you buy 5 pounds of coffee, it's $35. What do we think about that? So the options here are discrete, continuous, or neither. Based on what we've got here, does anybody have any thoughts? Discrete, okay. How come? What's that? Individual numbers, okay. Any other thoughts? Do we have any votes for like fully continuous here? Like, are we going to be able to connect everything and make a nice looking curve or line? No, okay. I see a lot of people saying no. Okay, so I think we can eliminate the fact that it'll be continuous. It's not continuous. I hear discrete, and I understand why. Does anybody think it could be neither? I'm gonna head over here for a second because off to the side, it says if you make a visual, oops, not there. If you make a visual, oftentimes it makes it a little bit easier to see what's going on. I know we don't have any like blank graphs on here, but I'm gonna use the right side, just underneath here, and make a little bit of a graph. So I'm gonna have an X, Y. I don't need negatives because negative pounds and negative dollars aren't a thing. So I'm just gonna go ahead and set up, this is not gonna be a nice clean graph, but it will give us a nice example of what this thing could look like. So we've got, let's just go X and Y. X is going to be the pounds, Y is going to be the cost, right? Okay. Now, if you don't buy any coffee, how much are you spending? 0. Okay. So we'll definitely have a point right there. Now, if you buy 2 pounds, how much money are you spending? 2 pounds is $8. Okay. So I need to go up to at least 35. So let's say, we'll just go by tens. So, and how many pounds are we talking about? Up to 5. Okay, so let's see. 1, 2, 3, 4, 5. So 5 pounds of coffee. And then each of these will be 10, 20, 30, 40, whatever. So if you buy 2 pounds, you're going to spend $8. So that'll be roughly there. Now, are you allowed to buy 1 pound based on the chart? It says up to 2 pounds is $8 per pound. Actually, no, that doesn't work. That would need to go here, because if you buy 2 pounds, how much are you spending? $16, yeah. So I need to move that to there. If you buy 1 pound, how much are you spending? $8. Okay, so then the 1 would be about right there. If you buy half a pound, how much are you spending? Can you buy half a pound? Yes. How much are you spending if you buy half a pound? $4. Okay, so that's going to be down right about there. Now, could I continue filling in with points in terms of the weight? There are other values that would fill in here. In fact, we can connect those. Because this is a sliding scale, right? A sliding scale in terms of up to 2 pounds. However, once you get to 2.5 pounds, it's just a straight $20. So 2.5 pounds is $20. That's right there. 3 pounds is $22, which is right there. 5 pounds is $35. So 5 pounds, 10, 20, 35, right there. And it does not offer anything in between in terms of those. So you can buy anything from 0 to 2 pounds, any amount in between 0 and 2 pounds, or 2.5 pounds, or 3 pounds, or 5 pounds. There's no values on there for 4 pounds, or 3.5 pounds, or anything like that. So that's what the graph actually looks like. So it's not continuous. Part of it is continuous. Part of it is discrete. So it's going to be neither. So this is where a visual can be a little bit helpful in terms of seeing what's happening. So let's head on back. Because customers can purchase any amount of coffee up to 2 pounds, the function is continuous over the interval x values between 0 and 2. Yeah. Including those values as well. You can buy no pounds. Obviously you can choose not to buy anything, and you can buy exactly 2 pounds. So we've got the or equal to underneath. So the interval, the x interval pounds between 0 and $2 is continuous. For larger quantities, top of the next page. For larger quantities, the coffee is sold by distinct amounts. This part of the function is what? If it's distinct amounts, discrete. So we have a continuous portion, we have a discrete portion. We can see that on the graph here. Since the domain and the range are made up of neither a single interval nor individual points, the function is neither. It's not discrete, it's not continuous. It's a mixture of both, which makes it neither. The domain of the function is any value between 0, 2, any x value between 0 and 2, including 0, 2, or x could be equal to 2.5 or what? 3 or 5, yeah. Okay, this represents the possible what of coffee beans? What are the x values relating to? Pounds, yeah. Possible pounds of coffee beans that customers could purchase. The range of the function, which would be the cost, between 0 and 2 pounds, what's the most expensive you're going to pay for 2 pounds? $16, okay, between 0 and 16, or 20, or what's the next one? 22, or $35. This represents the possible cost. We already talked about that, possible cost of the beans. So given a scenario, in this case, it's a sign for selling coffee beans, we can determine what kind of function we have. We can determine the domain and the range as well. Even though part of it is continuous and part of it is discrete, we can still write out the domain like this and the range like this. So the part that's continuous You have kind of an inequality and you've got values in between two numbers, and then the discrete portion is just those exact numbers. All right, now we're going to learn some new ways of writing domain and range and intervals. So far, this is what's known as algebraic notation. This is probably what you're used to seeing back from Algebra 1, things like that. We're going to have two new ways of writing things today. The first one is going to be called set builder notation, and the second one is going to be called interval notation. Some of you might have learned a little bit of interval notation in Algebra 1, depending on who you took for Algebra 1. Set builder will probably be new for everybody. So, set builder and interval notation. So sets of numbers like the domain and the range of a function can be described by using various notations. We've already done algebraic. Set builder notation, interval notation, and algebraic notation are all concise ways of writing a set of values. Consider the set of values represented by this graph. So we're going back to like really basic pre-algebra, Algebra 1 stuff, where we've got an inequality here in which x is less than 2. Right here, x is less than 2. So this is like the Algebra 1 way of writing it, or even pre-algebra. You probably saw this back in pre-algebra. We just say x is less than 2. So any value of x less than 2 works for this inequality. For set builder notation, it looks similar to algebraic notation because you're going to have that inequality as part of it. But we are going to include braces. That's what those little squiggly parentheses are called. They're called braces. The braces indicate the set, which you've used before, right here. Those are braces. So even back in Algebra 1, you've used braces before. Braces just indicate that you have a set of values. So the braces indicate the set. The symbol, that vertical line, is read as such that. So we're going to say all values of x such that x is less than 2. And then you're going to also see this symbol here. It's kind of like a capital E, but it's like curved with the middle line on the E as well. This is read as an element of. I'm going to give you an example here. So write this down. All real numbers. So this is how we would write it for algebraic notation, right? If it's all real numbers, we just write the words all real numbers. In set builder notation, we would say all values of x such that x is an element of the real numbers. This is how you write all real numbers in set builder notation. It's not an inequality because it's all numbers, but we start it the same way. If it's the domain, you go with x. If it's range, you go with y. And then the vertical line such that. And then the variable again for whatever one you're talking about, domain or range, x or y. The E, the curved E with the line in the middle means element of. If it's an element of something, that means it could be any value within this set of numbers. And all real numbers is every single number. And you might have seen this symbol before, the R with the double vertical line. That just means all real numbers. Back beginning of Algebra 1, when you were talking about different sets of numbers, you had natural numbers, whole numbers, integers, rational numbers, real numbers, irrational numbers, all those sets of numbers. This is the largest one of those sets because it includes all of them. And then the last one is called interval notation. And interval notation, the sets are described using endpoints. So beginning and end of where the numbers start and end. A parentheses indicates that an endpoint is not included on the interval. A bracket, if it's squared off at the end, indicates that the endpoint is included on the interval. Some of you might have seen this notation before. A lot of you probably not. So the way that we would write this one here is that, how far left does this go? To negative infinity. Yeah. So we're starting this set with negative infinity because that's how far negative it goes. Now there's a a parenthesis here because there's no such value that you can actually reach if you keep going that far because it goes forever. So you can't have a bracket. Bracket means you can stop. Parenthesis means it's not going to stop. And then you can get as close to 2 as you possibly can, but you're not going to include 2. So we use parentheses on that side as well. If it included 2, we would use the bracket. We'd square it up. So it'll take some practice for these notations. I feel like they're relatively understandable, but just keep going back to it and checking and making sure that things are written the way they need to. So we're almost done here. We only have a few more examples, and then, yeah, you're going to have a lot of time to work today. So set builder and interval notation for continuous intervals. Here we go. Write the domain and the range of the graph in set builder and interval notation. So for the domain, we're gonna practice this first one together, and I'm gonna have you do the next 2 on the next page on your own. So for the domain, this one goes left and right forever, which means that the domain is all real numbers. And since we just saw that one up here, I just wrote what all real numbers was. We're gonna say all values of x. We'd read this, all values of x, such that x is an element of the real numbers. That's our domain in set builder notation. Now the domain in interval notation, all the way left is negative infinity, all the way right is positive infinity. In which case, we don't have to write a plus for positive infinity. We can just write infinity. So it's sort of like using regular numbers. We wouldn't write -2 comma +2. We would just write -2 comma 2 if the 2 is positive. So for positive infinity, we don't put a plus. We just write infinity. So both of those things mean the exact same thing. They both mean all real numbers. Questions about the domain for set builder or interval notation? All right. Next one, the range. The least value of y for this function is? How far down does it go? -6. So the range is all real numbers greater than or equal to -6. So we have all values of y such that, what goes next? This part is this part isn't very similar to, this part is exactly algebraic notation. This part of set builder notation is the same as algebraic notation. So what are we going to write here? Y is greater than or equal to 6. Yeah, so y greater than or equal to -6. And just remember, if you're talking about greater than or less than, greater than, the open end goes towards the larger one. So y, open end to the y, line underneath it to include the -6. If it was less than, we'd flip it around. The pointed end indicates less than, pointed end towards something means less than. And then it actually just gives us the interval notation here. We've got from -6 to infinity. Now we are including -6, therefore we're using a bracket. Otherwise, we would just use a parenthesis, but because we're including -6, there's a bracket there. So all the way down to -6 and all the way up to infinity. And since infinity isn't a number, you can't really include that. So that's why there's a parenthesis instead of a bracket. All right. Questions so far? Okay, turn the page. I want you to try the 2 at the top of this page. Write the domain and range of each of them in both set builder and interval notation. I'm going to give you 2 minutes. So at 8:42, we'll check back in. Check in with the neighbors as well. Let's talk about set builder notation for this first graph. What's the domain? Let's just go ahead and say it using algebraic notation first. What would the domain of this be? What are our possible x values here? What's that? Everything, yeah, all real numbers. So the domain here is all real numbers. So set builder notation, let's see if you got it. We're going to say all values of x such that x is an element of the real numbers. That's our domain in set builder notation. Comma, get the range in there. So the range, you can always start domain and range with the brace and then the variable for domain and range and then the vertical line. So all values of whatever variable you're talking about such that, okay? What are we going to write for our inequality here? And it is an inequality because it's not all real numbers. What's our inequality for the range? Y is less than or equal to 3. Good. I feel like we saw that graph yesterday. Yeah, we did. It's right here. Here's at the top of page 4. That's the same one. So that is our set builder notation for domain and range. Now we're talking about interval notation. So we're using parentheses or brackets. We already know that it's all real numbers for the domain. So how would we write that in interval notation? First of all, am I starting with a parenthesis or bracket for the domain? Parenthesis. All right, because if we're talking about all real numbers, we're talking about literally every number. So there isn't an end or a beginning to the values. So we should be using parentheses on both sides. Now, because there's no variable here, it's hard to know if this is the domain or the range based on how we're writing that. So I might actually just say capital D dot dot for domain. Now we don't have to do those for the ones up on the set builder notation because we're using actual variables that correspond to domain and range, x and y, but here there's no x or y. So it's probably a good idea just to clarify which one is which. So there's the domain, all real numbers, negative infinity to infinity, comma, let's go capital R dot dot for the range. Is there a minimum value for the range? No. Okay. So what would the left side of our interval notation be then, Myra? Yeah, negative infinity with a parenthesis to the left of it. There is no least value here because it goes down forever. So we're going from negative infinity up to what number? 3. Are we including the 3? Yes. So are we using parenthesis or bracket? Bracket. Domain and range, set builder, and interval notation for that graph. Yeah.
How would you write it?
If what?
Like, when you're writing, how would you?
If it wasn't all real numbers, we would do something like that, depending on where the things are. In fact, example 7 will teach us that. So good question. All right. So let's go on to the next one here. What are the domain and range for this graph? All real numbers for both of them, right? All real numbers all the way across. So this one, let's make this one quick. All values of x such that x is an element of the real numbers, comma. All values of y such that y is an element of the real numbers. All real numbers for domain and range for this entire graph. Which means that in interval notation, we're going to say domain dot dot parentheses negative infinity comma infinity, close it off with parentheses, and then the exact same thing for the range. There we go. Set builder and interval, all real numbers all the way across. So in my opinion, today's part of the lesson is a little bit more straightforward than yesterday's part of the lesson. I don't know if you feel that way, but I certainly do. I definitely did when I was learning it back in high school as well. I always felt like one-to-one and on-to, I always got those mixed up. So that takes a little more practice, I think. Questions here? Cool. Now we get to talk about discontinuous functions and how to talk about domain and range for those things using both set builder and interval notation. I'm going to go back a page real quick just to show you. It gave us a little bit of info, but we didn't need it until now. But right here, this study tip on page 7, it says in terms of using symbols, you can use the symbol, the R with the double vertical on the left to represent the set of all real numbers. In set builder notation, we saw that already. In interval notation, this symbol here basically looks like a capital U, and if you just want to write a capital U, that's totally fine. Indicates the union, capital U, the union of two sets. So basically, if a function goes a certain amount, but then has a break and then picks up later on, you're going to use that union because you're going to say, from here to here, it's this, and then you're going to combine it with from here to here, it's this over here. We'll see what that looks like on the next page. Parentheses are always used because with positive and negative infinity because they don't include endpoints. There is no such thing as an end to those values. So this is the one that I wanted to focus on though right here. The symbol U. If you have a break or discontinuous function, you're going to have multiple domains and ranges because it's going to go from start to end, and then it'll have another start to end. And you need some way of like joining those two things, saying, hey, both of these things are part of the same function. So we're going to use this U in between them to indicate that there's a union between this part of the domain and that part of the domain, or this part of the range and that part of the range. So page 8, about halfway through, example 7. Write the domain and the range of the graph in set builder and interval notation. So we'll do this one together. I'll have you do the check one on your own. Then we're done with the notes, and you'll have the remainder of class to work. So you have probably about 20-ish, 15-ish minutes to work today, which is good. All right. The domain is all real numbers in relation to -1. So take a look here. There's -1. It's an open circle, and it's everything less than or greater than from this point here. Less than. So we're going to say x is less than 1. Are we including, oh, sorry, -1. Are we including -1? Yeah, it's an open circle, so we do not include it. So we're not going to put the or equal to underneath it. Or all values of x in what relation to 0? Greater than or equal, because it's a filled-in circle. So x greater than or equal to. I think it wanted us to use the words here, but I'm just going to go with the symbols. X is greater than or equal to 0. So Those are the symbols we're going to put here and here. Now you're going to notice a difference between how set builder notation and interval notation use either or union. And so try to make sure that you recognize the distinction there. But we're going to have x is less than -1 or x is greater than or equal to 0. And with set builder notation, we use the word or. Everything goes inside the braces. And we use the word or in between our two inequalities if there's some sort of discontinuity in the function. However, with interval notation, we write two sets of parentheses or a combination of parentheses and brackets or whatever it is. So from -infinity to -1, is that going to be a parenthesis or a bracket here? With the -1 parenthesis, yeah, because it's an open circle, so we are not including it. So parentheses. So you're going to have two sets of parentheses or two sets of brackets or combination of each of those two things. In between them is the union symbol. So here's the first portion of it. And it is being unioned with everything from 0, including 0 with the bracket, to positive infinity. And positive infinity also uses a parenthesis. For the range. The range will be all real numbers in what relation to -1? Here's -1 on the y-axis, going down, so greater than, less than, greater than or equal to, less than or equal to, less than. I'm gonna write the words this time, less than. You can do the symbol if you want to. And then here's +2 on the y-axis. Are we including it? Yep. Is it going up? Yep. So greater than or equal to 2. So set builder notation, less than -1, or y is greater than or equal to 2. And we need the brace to the right side of the 2. In terms of interval notation, we're going from -infinity up to -1. We are not including -1 though, so parentheses there. And that is a union with 2 up to positive infinity. Greater than or equal to 2, less than -1. All right, last one. I want you to do that one on your own. Write the domain and range in both set builder and interval notation. have a look. So our domain would be x is less than -1 and, or x is greater than or equal to +1. So for set builder notation, we're looking at all values of x such that x is less than -1 or x is greater than or equal to 1. There's the domain in set builder notation. For the range, we've got all values of y such that y is less than 1 or y is greater than or equal to 1. I'm going to come back to this one. If you wrote it like this, you're good, but we are going to talk about this one in just a second. Not the domain, but we will come back to the range. Then for the domain here, we've got, I'm going to put D for domain, and this is going to be -infinity to -1, parentheses around both of them, and then the union symbol, capital U. Then we're going to go with a bracket, 1, comma, infinity. That's the domain. Any questions so far? I'm going to hold off on the range for a second. Any questions at this point? Okay. Now, the reason I want to come revisit this here, any thoughts about why I might want to come back and revisit the range here? You notice anything about the range? How it's written or how it looks? Is there a gap in the range? There's definitely a gap in the domain, right? It stops here, it picks up over here. Is there a gap? So domain, definitely a gap. Range, is there a gap? There's not actually a gap, is there? Because if there was a gap, this one would go to about here. Then there would be a gap in the range, but there's actually an overlap. Right? This from here to here overlaps from here to here in terms of the range. -infinity to +1 overlaps with -1 to +infinity. There's an overlap here. So what does that tell us about the range? If there's an overlap, and the overlap includes all the numbers in between it, the range is all real numbers. Every single value of y is part of the range here. It's in different sections in terms of the x value, but in terms of the y value, there's overlap between them. So any value of y does work for this graph. That's why I held off on the range down here, because the range R is going to be -infinity to infinity. Because we have overlap. There's no overlap with the domain, but there is overlap with the range, and that overlap includes everything that was missing from one part of it to the other, which means that every y value works. All right. So that's all we got. We got about 12 minutes to continue working on the assignment. The assignment is 1 through 39 odds. Remember that you can check your answers in the back of the book, but that also means that you need to show work for every single problem that you can show work for. That way I know you didn't just go to the back of the book and write the answer down. So get working on that. Feel free to move around and work with each other. Yeah. Yeah, so tomorrow, this will be due tomorrow. If you use any extra paper, staple that extra paper to it. And these pages are perforated. There's a dotted cut already there. It makes it easy to remove the pages. If you want to remove the pages now and just work on them like that, totally fine. Just make sure you write your name on it and that you staple it together when you turn it in tomorrow. We will go over all the answers first thing tomorrow. And then if there's questions, we can address questions, and then we'll start in on lesson 1-2. So keep working.